Thanks very much, John. That was a nice introduction. And welcome, everybody. And thanks to my co-authors who've been very helpful in... I'm just getting used to this new pointer. Interesting, isn't it? They helped me put together the material for this presentation, and I'm hoping they're going to help me produce the manuscript for submission to the Royal Society. What I want to do in the next 20 minutes or so is to explain how air quality became a larger issue. It started in urban areas. It grew into regional scale problems, acid rain and then photochemical smog. And the photochemical smog is not just restricted to Europe or North America, it's actually hemispheric in scale. So it has become a global issue. And then the point at which Europe and North America began to introduce controls, just as emissions were growing in China and India. And I need to say a little bit about air quality and climate. Climate is such a huge issue that it needs commenting on, but our presentations over the next 2 days are primarily on air pollution, so that link just needs to be mentioned, and it'll appear in several talks. And then a few policy points to make about the point at which decisions are made to introduce effective controls, and then some concluding comments. So if we go back quite a long way, Hippocrates said that if you want to learn about the health of a population, you look at the air they breathe, the water they drink, and the place they live. He recognized in some of his philosophical comments that air pollution was a problem for human health. And another philosopher, the Roman Seneca in AD 61, he said that as soon as I had left the air of Rome and from the stench of the smoke of chimneys, which emitted pestilential vapors and soot, I felt a change in my disposition. And this link between human health and air pollution will be a major feature of our discussion over the next 2 days. But you have to move forward quite a long way in time before you see something written in quite graphic detail. This is John Evelyn, one of the founding fellows of the Royal Society here in London, and he wrote this document called Fumifugum, and you can Google it and read the whole document, 38 pages. What he said about London was that this glorious and ancient city should wrap her stately head in clouds of smoke and sulphur, so full of stink and darkness, I deplore with just indignation. I've captured some of the words in the documents that you can read there, just to give you a flavour. Now, this is very colourful language, and it's probably more familiar to those listening to debates in the Houses of Parliament than in a scientific society such as this. But I thought, reading the document, that there would be some quantitative information. And those 38 pages contain no graphs, no figures. The only numbers are the page numbers and occasional dates. But if you move forward just a year to 1662, John Graunt, who was also a Fellow of the Royal Society, wrote a document upon the bills of mortality, essentially life tables, and he provided statistical links between great stinking fogs and human mortality. And what he observed, if I can make this thing work, he observed that during the big fogs, more people died. He was primarily interested in human disease, but he had established quantitative links. We knew then, by the 18th century, that air pollution and mortality were linked. But there's a problem with this data. Statistically, you need to know what the pollution is. There were no measurements of the gases present or the concentrations of particulate material in the atmosphere. So it's a very important early observation, and it's quantitative, but it doesn't tell us much about the chemical nature of the pollutant threat, and we'll learn a lot about that over the next 2 days. But all of these early pieces of evidence, they're all local. They're all town centres or close to sites of smelting or lime kilns, which were very common in the countryside. There was nothing that operated at a regional scale except volcanoes. There were volcanic events that had a regional footprint. And in 1783, the Laki volcanic eruption in Iceland, a very big eruption, produced large concentrations of sulfur across the northern parts of Europe. This is a computer simulation from Annie Schmidt, and she showed very large concentrations here, 20 to 100 parts per billion by volume across northern Europe. And during that event, there were widespread effects on human health in Europe and some noted in North America. So with the exception of volcanoes, nothing much happened until we came to the Industrial Revolution. Two images here of northern English cities in the height of the Industrial Revolution. And there were laws, and we spent some time in putting this material together to look at some early laws. The first environmental protection laws in China, they were general. They weren't focused on air pollution. They were in 200 BC. The first air quality legislation was in London in 1306, when Edward I banned the burning of sea coal in London. Well, that worked well, didn't it? And many early examples of laws, and we've trawled several countries, UK Smoke and Nuisance Acts in 1853, 58, 66, and in the USA, some very important legislation in 1881 and in France, 1810. There's tons of legislation out there. The lawyers did their diligent work, but it didn't have any significant effect. The rapid industrialization of Europe and North America degraded air quality very rapidly. So most cities became very polluted. And it wasn't just the quality of the air. The pollution is reflected in our literature and art. So if you read Dickens and Conan Doyle in the UK or Ibsen, pollution actually figures quite heavily in the manuscripts. And artists flocked to London to paint the landscapes. Monet made some famous paintings of London in fogs. And there were early measurements by Robert Angus Smith, this famous text, Air and Rain, the Beginnings of a Chemical Climatology. That really provided some useful information, but it didn't allow us to see the chemical nature of air and rain across Europe. There was nothing significant until the 1950s by way of a European network of measurements. So if we now look at the emissions of sulfur between the start of the Industrial Revolution and the peak of emissions. The peak of emissions was in 1970, about 130 teragrams per year. And up to that point, 75% of those emissions were in Europe and North America, and 90% of the emissions occurred in the 20th century. So the sulfur problem was Europe and North America and a 20th century problem. It really didn't get going until then. And just to illustrate the scale of the concentrations, in England, for example, almost all the major cities, all those cities in black or red, had concentrations between 60 and 100 micrograms per cubic meter of sulfur, and it extended over the landscape. And you might wonder why I've pasted this image on the right-hand side. Towards the end of the Victorian era, there were massive populations of horses in all the major cities. London had 50,000 horses. New York had 100,000, producing 1,000 tons of manure every day, which all had to be scraped off the streets. And the importance of that for air quality is that it was emitting large amounts of ammonia into an urban atmosphere. So we had large amounts of sulfur dioxide, large amounts of ammonia, large amounts of NO2 and smoke and particulate material. And all of this came to a head in the UK in 1952 with the London smog, when huge concentrations of sulfur, almost 2,000 micrograms per cubic meter and 1,600 micrograms per cubic meter of smoke, led to 4,000 early deaths. Now, Michelle Bell, who is our next speaker at the meeting, reanalyzed these data, and the number turns out to be much closer to 12,000 deaths. Now, this was a very important event, and it was very important in a policy sense because air pollution and smogs had been a very common feature of London. London was called the smoke, but it was only after this event that the Clean Air Act was developed and passed Parliament. In fact, it wasn't the government of the day that was the champion of this bill. It was a backbench MP, Gerald Nabarro, who eventually got sufficient support to push it through Parliament. And the principle of this bill was to take the coal burning out of the city, both from domestic and industrial, and move it into the countryside. So we take the power stations and we build big power stations into the countryside and shut down those power stations, some famous ones in the middle of London, for example. And it took some time to clean up the air. Sulfur dioxide concentrations declined to about a half in 15 years, and then again by another half in another 15 years. So it took 30 years to really take away most of the sulfur and smoke. And this gives the impression that London has a much cleaner atmosphere now, down here, compared to this 1960s and 1970s. And you'll hear in later presentations that London still does not have very clean air. So things have changed greatly. But that period of big emission reductions was one in which there was a network of measurements of air chemistry across Europe from the Swedish European Air Chemistry Network, a nice network of sites. And what they observed was that over the first decade, the rain became much more acidic. So here, acidity had increased by a factor of 3 or 4 in a relatively short period. And during that period of the 1960s, Swedish scientists noted that their lakes were becoming more acidic, the fish populations were disappearing rather rapidly, and this man, Svante Odin, advanced the very radical hypothesis that that acidification was due to imported sulfur from the industrial countries, UK, Germany, especially, and Poland, landing on Sweden. Now that was a very radical policy, and he was criticized heavily by his academic colleagues in Sweden, because we didn't know all of the facts. But over a 2 or 3 year period, some of the basic numbers were put together. We know that the sulfur is emitted as a gas, and likewise oxides of nitrogen, and that's oxidized through to particulate material, which generates acidity, and that stuff rains out at some distance from the source. And over 3 or 4 years, Sweden put together a very persuasive case that they shouldn't be receiving problems from other countries' emissions. And they had a conference in Stockholm, Sweden's case to the United Nations Conference on the Human Environment in 1972. And this, like the London smog, in a policy sense, was extremely important because it was the recognition that international exchange of pollutants across Europe was a major issue, not just scientific, it was political. And it led to the control of sulfur across Europe. And we'll hear much more about that in the policy framework in a presentation later this morning. Of course, the air had been blowing this pollutant around Europe for some years. It was only that point in time that it became clear that something had to be done. If we look at the emissions on a map, you can see for example, the shipping track through the Mediterranean. This is shipping emissions of sulfur. You can see the big industrial countries, UK, France, Germany, Poland. And Scandinavia looks rather clean. It was receiving most of its pollutant in rain. But there were also countries in the centre of Europe, the Black Triangle, right at the heart of the pollutant concentrations, lots of sulfur, lots of oxides of nitrogen, ammonia. And on the high elevation areas of the border between the Czech Republic and Poland, forest declined very rapidly. So forest decline became an issue after the initial observations of acid rain and fish in Scandinavia. And it wasn't just limited to Europe. North America had its problems. Those brown colors are the greater acidity in the east of the US. The ellipse there shows the Ohio River Valley, where most of the air pollution was generated, power stations and most of the industry. And the second ellipse is where some of the sensitive ecology was, where the lakes were becoming acidified in the New England states and in eastern Canada. So the fact that it was in Canada was very useful politically, because the US was polluting its neighbor, just as the large industrial countries in Europe were polluting Scandinavia. So if you turn to those periods, acid rain was about ecosystems. The ecosystems effect, fresh waters and fish, Europe and North America, and the acidity was mainly sulfur. Forest decline came a little later. It had more elements than just acidification, and we'll hear more of that in later presentations today. And eutrophication, the deposition of reactive nitrogen on the landscape, essentially the atmosphere fertilizing the semi-natural flora of Europe and its changing species composition. We'll hear more about that. But they weren't the only problems of regional scale air pollution. If we go to photochemical smog, this was associated in the middle of the 20th century with Los Angeles. But that ozone and the other products of the smog generated through the degradation of VOCs photochemically in an atmosphere containing oxides of nitrogen, it's a hemispheric scale problem. This is a satellite remote sensing image showing high ozone right the way across North America, Europe, and Asia. And the lower panel is a chemistry transport model showing that our understanding of the processes are sufficient that we can simulate it with computer models that operating at a global scale. So we have now, in addition to acid rain and eutrophication, ground level ozone operating at a hemispheric scale. So what do we do? There was sufficient momentum in the political process to reduce emissions. And if you look at today's emissions, sulfur has been reduced in Europe by 90%. In the middle there, we've got oxides of nitrogen and VOCs. They've gone down by about a half. And at the top is ammonia. That's been reduced by about a quarter. So Europe has made quite big steps in the reduction of the primary emissions, likewise North America. And as a result of that, acidification pressure has declined substantially, comparing here 1990 with 2010. The results of this is that ecosystem acidification is recovering. There is still quite a lot of nitrogen, and we'll hear about that in later talks. The reduced NOx and VOC has reduced peak ozone in Europe and North America, but the average concentrations haven't changed very much. Now, that's the background to Europe and North America. If you look globally, bringing it up to date, you see that the pale blue and the dark blue have shrunk hugely, but emissions in China and the rest of Asia have compensated, so that globally sulfur emissions have only declined by about 15%. So globally we still do have a sulfur problem. And if we look at oxides of nitrogen, we are probably at about the peak at the moment. Despite big reductions in Europe and North America, emissions elsewhere in Asia place us very close to as large an emission globally as we've ever had. And for black carbon and for ammonia, they're also showing no signs globally of a decrease. It looks from the satellite data as though we've reached the peak for black carbon, but ammonia looks as though it's going to continue rising for some years to come. So globally, pollutant emissions are increasing for some pollutants, and they've clearly peaked for sulfur, and we are at the maximum for NOx and VOC. Now, while all this was happening in Europe and North America, the epidemiologists were continuing to look at the link between human health and mortality, not just in the periods of smogs. This famous paper, published in 1993 by Dockery and his colleagues, showed a very important relationship between PM in the atmosphere and mortality. That changed the priorities politically. Because human health can be costed and because it's politically very sensitive, it has become the dominant issue globally. And even with those pollution emission reductions across Europe, human health loss, deaths due to particulate matter across Europe, the black and the dark red colours are something like a couple of years of life lost due to particles smaller than 2.5 microns. The right-hand panel is something that doesn't appear in the press reports daily. You do hear about human health, but the exceedance of critical loads for nitrogen, they continue. Vegetation is still receiving, across most of Europe, far more nitrogen in semi-natural areas than it can easily cope with. And those species that have adapted to a very limited supply of nitrogen are disappearing. So if we look globally now, global and regional networks show us our concentrations. We've got very good satellite monitoring and a whole suite of models. These satellite remote sensing can see most of the primary pollutants and the secondary ones, ozone and aerosols. And just to illustrate some of this, you can see, for example, with satellite data between 1996 and 2002, you can see the reductions of NO2 in Europe. You can see the growth in China. You can see on this panel here, it's very large ammonia across the Indian subcontinent, in China, and coming around from North America. You see the agricultural emissions in the western states and also ammonia in the Amazon, across tropical Africa, Europe. Satellite remote sensing is becoming a vital tool to support the estimates of emissions across the planet. You can also see particles, the big numbers across China, India, and North Africa. And just turning to sulfur, you see the hotspot of sulfur up there in China. It's important to note that Chinese emissions have declined. This is the emission inventory. China has halved its sulfur emissions in about 8 years. Europe took much longer, 3 times as long, really, to reach those kind of reductions. And NO2 has gone down by 20%. And so those are emission estimates. But if you look at the satellite data, using lots of satellites data put together, you can see that the satellite data show that NO2 decline quite effectively. So the combination of emission inventories, satellite data, and surface measurements means we have a very good picture of the major polluted regions. A little bit about regulations and laws. They're not the same in each country. The areas in green, the countries in green, have air quality standards and they have policies to control air pollution. The ones in yellow have one or the other, and the ones in red have neither. And the point I want to make here is that you can have the best science in the world, but the policy decisions are taken according to the conditions in the country, the state of economic development, and the priorities for the governments. And Kuznets demonstrated that in a pre-industrial economy, the environment generally degrades, whether it's water or air quality. And we only introduce measures to control the air once a certain level of affluence has been achieved. And the point I want to make here is that we do need the science, we need the measurements, and we need the information. But once that's been assembled, the decisions are not taken by scientists, they're political decisions. And if you look at some of the changes that have taken place as Europe and North America have moved more to a service economy and lots of the manufacturing of stuff moves to Asia, then the pollution generating from that manufacturing takes place there. And maybe that will happen for Africa too. That's just a speculation. Just a quick word on global air quality and climate. These are emitted by the same sources. So if we look at this very familiar table to you from the IPCC, you see that CO2 is the major radiative-forcing gas, but methane is at the heart of ozone production, so it's very closely coupled to air pollution. Likewise, volatile organic compounds and NOx, they're involved in the production of ozone and also particulate matter. So it's important to develop an assessment of air quality and climate change in a common framework to avoid win-lose policies, such as promoting the use of diesel vehicles to assist climate change at a time when those vehicles are producing lots of NOx and particulate matter. And just a few concluding remarks before inviting some questions. We look as though we're at the peak of poor global quality at the moment, global air quality at the moment. Sulfur emissions are declining. NOx looks to be just past the peak. Ammonia remains a problem and it is rather poorly controlled everywhere. And likewise, VOC looks as though it's going to continue. Does Africa have to go through the same degradation of air quality we've seen in Europe, North America, and Asia? And on nitrogen, we know that we've reduced emissions of the oxidized form and to a certain extent reduced, but we're still depositing far more nitrogen than natural ecosystems can comfortably cope with. And ozone remains a threat to human health, biodiversity, and food security. And on particulate matter, I've put it in bold because it is in a policy sense, the major problem. So despite the successes of control in Europe and North America and elsewhere, there's a great deal to do. And I'll stop there. Thank you.
Thank you very much, David, for a really nice introduction to this meeting. Can I ask for questions from the floor? If you have a question, can you use the microphone? And perhaps you could say who you are as well.
Kevin Kendall from Adelan in Birmingham. Would you say that London is leading the way in this endeavour to clean up the atmosphere?
Be nice to say yes. If you look at the headlines, you would not get that impression. There are still very significant air pollution problems in London, but it is showing leadership by controlling vehicles and sources, by having very sophisticated monitoring networks and getting to the heart of understanding the problem. There is a considerable leadership.
One right at the back.
Thanks very much. My name is Rob Hughes from the Clean Air Fund. I wondered if you could start to answer the question that you posed at the end about whether what's your sense on the data that we have at the moment about whether Africa is likely to follow that trend that Asia and Europe have in terms of increasing toxic air and then a later decarbonisation and detoxification, or do you think there's an alternative trajectory? What are the early signs on that?
It's a good question, but I'm not an expert on what's happening in Africa. I observe that if you looked at the population changes globally, it's the one part of the world population changes are extremely quick. And there is also a migration of people into cities. So the people exposure side of it is going to get worse, for sure. But on the positive side, if we look at what's happened in China, China's clean up or is cleaning up much faster than Europe or North America did. So the fact that we have such good instrumentation and a knowledge of the problem means that they should be able to learn. So I take a slightly less gloomy view than I might have done if you just looked at historical evidence.
Yeah.
I'm Ian Boyd from University of St Andrews. I'm going to take issue slightly with your conclusion that we are potentially cleaning up, because I think that there's a chance that we might simply be moving the problem from one with strong feedbacks, with clear causation, to one with much weaker feedbacks in terms of our capacity to understand the causation. So we simply move the emissions from sulfur through to, for example, methane and carbon dioxide. Do you think that that's a process which is actually happening, or would you contend that we are actually cleaning up?
Well, if you treated the pollutants one by one, the evidence is irrefutable that we are cleaning up sulfur. And it looks as though on oxidized nitrogen, if you look at the latest generation of vehicles, once they migrate into the fleet, we'll continue to see a decline of NO2. I think your point is right on methane and CO2. Methane is such an obvious target because it's such an important greenhouse gas and it's right at the heart of air quality problems. It would be an absolutely perfect target to really go for. But globally, methane emissions are increasing. So I think you're right in the thesis. I think policymakers haven't taken methane anything like seriously enough.
I have one more question. There's a hand there, yeah.
Thanks, David. Gary Fuller from King's College London. Our perception of air pollution is very much shaped by the way in which we measure it. And for the first half of the 20th century, we generally only measured the black stuff in the air. but there has to have been emissions of sulphur, and you made a prevailing case for emissions of ammonia, certainly in urban areas. Do you have any ideas or parameters as to what the secondary aerosol would have been like during the first half of the 20th century?
Yes, it's a very good question. There must have been enormous concentrations of secondary aerosols in urban areas. All the few measurements we do have show massive numbers, but all they measured was this optical blackness or the mass of material in a plastic rain gauge or a glass rain gauge. I think there's more work that could be done there, but in trying to provide numbers for ammonia, I consulted some of my colleagues, and we differ over how big the ammonia concentrations were, because their simple box model said it was a few micrograms per cubic meter. But 1,000 tons of horse poo on the streets makes me feel the numbers per day must have been much larger. There must be some evidence of some of these early pollutants, but I don't know who's going to come up with it.
There's another one there, and then...
James Allen, University of Manchester. Just speaking to the point on your conclusion side where you put in bold about how important particulate matter was. Obviously, a lot of the policy-making effort, particularly on local scales in the country at the moment, is currently on nitrogen dioxide, primarily because of the exceedances and so on. Are you implying that perhaps the energies may be misdirected in that regard and we should really be focusing on PM?
Yes.
If there are no further questions, I don't see any more hands. Let's thank David again.